Hello everyone, my name is Jamilya Nurgazina and I'm presenting our paper today titled Visualization and Clustering for Rolling Forecast Quality Verification, a case study in the automotive industry. In today's presentation, I will present the content of our paper, including the introduction and the research questions to be addressed in our study, the methodology and the case study results, and finally, the key implications and limitations of our study presented in the paper. Finally, the Q&A session will conclude the presentation. In this paper, we describe one situation in automotive manufacturing environments when two stakeholders in the supply chain, a manufacturing company and its customer, which is a car manufacturer or first-tier supplier, share material and information flows in everyday situations. The manufacturing company provides the materials to its customer, and the customer provides the information on its own demand to the manufacturing company. The information flow includes the forecast data provided by the customer via the EDI on a rolling horizon basis, meaning that the customer orders are provided on a recurring basis, for instance, once per week. The problem that we are addressing and that we are describing specifically is the problem of not storing and utilizing the historical information of the forecast customer demand. And this is a specific company situation that we are addressing in this paper. The result of this situation, when the manufacturing company and its customer exchange forecast information details on a weekly basis, the data is updated on a recurrent basis, rewriting the previous forecast information. Therefore, the historical data is not saved, and therefore it's not utilized for future use. Hence, the process and production inefficiency occur, resulting in the inefficient use of resources, inefficient production planning, and the related production processes. To address this problem, we investigate the forecast error measures that can help to address the problem of the forecast uncertainty and judgmental forecasting, which subsequently lead to the bullwhip effect. With various visualization and clustering techniques, we analyze the forecast data consisting of multiple products and its forecast evolution to improve the existing production planning and forecasting processes. We develop a prototype combining visualization and clustering techniques in a web-based platform. Our analysis and results are presented in a case study analyzing the clusters of similar forecast behavior which are identified from the provided dataset. Finally, some managerial insights are elaborated to improve the forecasting and planning processes. We are addressing 3 research questions in our study. The first research question is, which forecast methods and visualizations are useful to analyze the quality of customer-provided forecasts, and what are the limitations of the analysis for a real company? The research question 2, how can clustering methods be integrated to analyze forecast evolution of multiple products? And finally, the research question 3 is, what managerial insights for improvement of forecast accuracy can be elaborated based on their clustering results? Here, the methodology of our approach is described. In this table, the data structure of the forecast updates provided by the customer company is presented. The orders are highlighted in a gray color, where the darkest shade represents the final customer orders. The orders on the left side of the darkest diagonal are the forecasts. The J notation here represents the periods before delivery, and the T represents the calendar weeks or the time units of the forecast updates. For instance, the forecast update, which was sent in the calendar week 48, is highlighted in a green color. So here we can see that the forecast update, which was sent in the week 48, represents the order amounts of 640, 880, 880 and 720 pieces for the next 4 weeks, where 720 pieces is the final order. And if we want to see the forecast evolution behavior, we need to look at the vertical side of this table, shown in the blue color, representing the different forecast updates for a specific forecast week, for instance, the week 49, as shown in this example. On this slide, we see a screenshot of our prototype, which includes the visualization and clustering techniques, including various types of visualizations available. This example depicts a single product analysis, meaning that only one product data can be visualized with these types of visualizations. And since such visualization is limited and multiple product data cannot be properly visualized here, we implemented different clustering techniques in our visualization prototype in order to implement a multiple product analysis in a semi-automated way. In the visualization tool, we implemented 3 clustering algorithms. Affinity propagation algorithm is the algorithm that detects the number of clusters automatically on its own, and it detects the representatives in a data set based on numerical similarities between the data pairs. K-means, on the other hand, needs the number of clusters to be defined by the user, and it allocates the clusters respective to the closest centroid in a data set. And finally, the agglomerative or hierarchical clustering is a bottom-up approach which merges the objects into larger clusters iteratively according to the minimum distance to each other. The clustering algorithms allow to detect patterns in forecast data and allocate product groups into different clusters, therefore enabling a multiple product analysis with a high number of products. So to apply our approach in the methodology in a real example, we carried out a case study in an automotive sector in Austria. We collected 6 months loan forecast data from an automotive supplier, which consisted of historical forecast data that was not stored in the ERP system. In this approach, the forecasts were updated and overwritten with customer order details each Sunday, recording new forecasts of the next 15 calendar weeks. The data originally consisted of 78 products. With the ABC analysis, we shortlisted 33 products of the highest importance for the production planning of the company analyzed, and therefore we analyzed 33 products in our paper and in our detailed analysis with visualization and clustering techniques. First, we implemented a single product analysis, which can be addressed with simple scatter plot visualizations and a heat map-based matrix visualizations, which can be seen on this slide. The scatter plot visualization on the left-hand side, which is the figure A, represents the forecasts and final orders, where yellow circles represent the forecasts and the blue stars represent the final orders. In this example, when one product data is visualized, this is straightforward and it can be seen how the forecasts are distributed comparing to the final orders with respect to the due dates or forecast periods. While with the matrix-based visualizations on the right, we can see in the heat map visualization how the amount of forecasts varies with respect to calendar weeks. The color here also provides a hint depicting the order amount variation, showing a darker shade when the order amount is higher and a brighter shade when the amount is lower. The diagonal here represents the final orders. And here we can address the research question 1. With these kinds of visualizations, we see a limitation with a multiple product analysis when it is no longer visible whether there will be multiple products and also how to differentiate between the different products. In addition to the visualizations shown in the previous slide, we also implemented the visualizations of the forecast error measures, which also work mainly for a single product analysis. In this example, we introduce an error measure called mean forecast bias, shown as a scatter plot with respect to periods before delivery, with period before delivery 0 being the week of the final order. Mean forecast bias is defined as 1 plus mean percentage error. This visualization provides an overview of how the forecast accuracy varies with respect to periods before delivery, with an average line shown as an orange dashed line representing the average value of all mean forecast bias calculations in this graph. For multiple product analysis, this kind of visualization is limited. For instance, this does not work for 200 products in a data set. Therefore, other approaches had to be applied in order to verify the multiple product analysis. So we introduced the multiple product analysis with the clustering algorithms. In our approach, we implement a single framework in a prototype combining visualization techniques with machine learning algorithms in a web-based platform. The visualization tool is a web-based tool for companies participating in our research project to analyze their historical data. This prototype is connected to a MySQL database where all forecast data is stored. The clustering part consists of 3 clustering algorithms described previously: the affinity propagation clustering, k-means, and the hierarchical clustering, which were implemented with scikit-learn and tslearn Python libraries. The visual analytics part was implemented with D3 JavaScript library, Pyadite, and a cross-filter JavaScript library, and consists of 3 parts, which are classical order analysis, targeted mainly at the single product analysis, forecast error measures visualizations, and a dashboard, which combines the visualization of all forecast error measures on the one page. Addressing the research question 2, we can address this question by implementing a clustering technique with machine learning algorithms in our integrated framework to address the aspect of having multiple products in one dataset. So in the case study we conducted, we identified 7 clusters, which are presented in this slide, with affinity propagation clustering, which allocates the number of clusters on its own. In total, we had 33 selected products in our dataset. In these clusters, we see how the different forecast behavior varied with respect to periods before delivery and analyzing mean forecast bias as a key criteria. We can distinguish already different types of forecast behaviors in the provided dataset. Analyzing the clustering results, we identified that each of the clusters could be allocated to a specific behavior characteristic. For instance, we can see that the clusters 1 and 2 were the biggest, with 10 products in each of them. And they had the unbiased forecast evolution behavior, meaning that no specific behavior could be allocated to these 2 clusters, and there was either moderate or high mean forecast bias deviation. While all the rest clusters 0, 3, 4, 5, and 6 had distinguishable overbooking behavior, meaning that the forecast amounts were primarily higher than the subsequent final order amounts in this specific example. To address the research question 3, we can state that for clusters 0, 3, 4, 5, and 6, the application of forecast correction models is suitable due to the fact that a specific overbooking behavior was present. While for the clusters 1 and 2, no correction models should be applied due to the fact that no specific or unbiased forecast evolution behavior was detected in these clusters. Finally, we elaborate on the key implications and limitations of our study. In our paper, we presented a new forecast error measure called mean forecast bias to address the issue of the forecast uncertainty. We identified and presented single product versus multiple product analysis in a case study in an automotive industry in Austria with various visualization and clustering techniques. It was shown that in the case of systematic over or underbooking behavior, self-calculated forecasts based on historical final order amounts can be applied with forecast correction models. While in the case of highly fluctuating or unbiased customer demand with no systematic tendency shown, other approaches such as higher safety stock or higher reorder point levels could be adapted. The affinity propagation clustering was shown to be useful for the multiple product analysis of the forecast data, in this case identifying 7 clusters of different forecast evolution behaviors out of 33 products. The findings of our paper are relevant for the automotive industry in production planning environments when the forecasts are updated on a rolling horizon basis, which limits the scale and approach of our analysis. Also, due to the specific requirements for the data preparation that had to be met to be implemented in our prototype with the visualization and the clustering approaches, there is a limitation that not all datasets can be suitable for such approach, and some data preparation guidelines have to be met to make such analysis possible. Thank you very much for your attention, and please feel free to contact us for any questions.